Voyager 1S, last gasp the fight to hear humanity's farthest whisper. Billions of miles away, in the absolute dark, a machine built in the 1970s is slowly dying. Voyager 1 is humanity's farthest emissary, but its power is fading, and soon it will go silent forever. This enduring whisper represents our deepest reach into the cosmos, providing unique insights from the heliosphere's edge that reshape our understanding of the universe. We delve into the intricate battle against fading power and astronomical distances, exploring the continuous operational adjustments required to sustain this remarkable mission. These critical challenges and ongoing efforts are meticulously managed through deep space communication protocols at the Jet Propulsion Laboratory. Voyager 1 stands as an unparalleled testament to human ingenuity, an explorer launched over 4 decades ago, now charting the deepest frontiers of space as humanity's most distant ambassador. This venerable spacecraft, part of the original Grand Tour concept that envisioned journeys to the outer planets, far exceeded its initial design life and mission parameters, eventually transitioning into an interstellar mission. August 2012. The instruments registered a sudden shift in cosmic rays. Voyager 1 had crossed the Heliopause. He left the protective bubble of our sun and entered the dark, unforgiving void of interstellar space. This historic entry marked a profound shift in its scientific mandate, providing humanity with the first direct measurements from beyond our star's protective bubble, a feat previously confined to theoretical models and remote observations. The enduring paradox of Voyager 1 is that while it remains technically alive, sending back invaluable scientific data, it is simultaneously engaged in an inexorable decline, a slow fade into silence. Its operational vitality is defined by its ability to generate power, maintain directional antenna lock with Earth, and transmit telemetry. Yet every passing day brings it closer to the inevitable end of its operational life. From the critical vantage point of deep space communication, this mission presents a unique set of challenges that push the very limits of our technological capabilities. The sheer scale of Voyager 1's distance, currently over 24 billion kilometers from Earth, introduces a profound time lag in all interactions. A radio signal, traveling at the speed of light, takes approximately 22.5 hours to reach Voyager 1, and its response another 22.5 hours to return. This nearly 2-day round-trip communication delay necessitates an entirely different approach to mission operations, requiring meticulous planning, pre-programmed command sequences, and a reliance on onboard autonomy, as real-time intervention is simply not possible. Maintaining this fragile communicative link across billions of kilometers is an extraordinary feat of engineering and precision. The signal transmitted by Voyager 1 from its 3.7-meter high-gain antenna, powered by just 23 watts roughly, the output of a refrigerator light bulb diffuses across such an immense distance that by the time it reaches Earth, its power is measured in fractions of a picowatt. To detect and decode this whisper from interstellar space, the Deep Space Network DSN facilities, strategically located in Goldstone, California, Canberra, Australia, and Madrid, Spain, employ massive 70-meter parabolic antennas. These gargantuan structures, operating as global ears, are equipped with cryogenically cooled receivers that minimize thermal noise, enabling them to capture the incredibly faint signals. Advanced signal processing techniques, including sophisticated error correction coding, are then utilized to reconstruct the data streams from what is essentially background noise. Historically, the DSN has continuously refined its capabilities, adapting its algorithms and hardware to maintain contact with distant probes, a testament to decades of cumulative expertise in radio science and telecommunications engineering, as frequently detailed in technical briefings from the NASA Jet Propulsion Laboratory. The very ability to discern scientific instruments, readings such as plasma wave data, magnetic field strength, and cosmic ray intensity from such a minute signal is a crowning achievement in radio astronomy and communication. Each packet of data received from Voyager 1 is a treasure, representing direct measurements from a region of space no other spacecraft has ever reached, providing critical insights into the nature of the interstellar medium and the boundary that separates our solar system from the wider galaxy. Voyager 1 represents an unparalleled triumph of human ingenuity, navigating the most distant frontiers of space, while maintaining a fragile yet vital communicative link across billions of kilometers. The formidable endurance of Voyager 1, while a testament to its robust design, confronts the relentless and inevitable realities of deep space operations, primarily driven by the mechanics of its mission decline. At the heart of its sustained functionality lie three radioisotope thermoelectric generators, or RTGS, which have faithfully powered the spacecraft for over 4 decades. Unlike solar panels, which are rendered ineffective at such vast distances from the sun, RTGs generate electricity through the natural radioactive decay of plutonium-238. This process produces heat, which is then converted into electrical power via thermocouples. However, the radioisotope fuel undergoes a continuous, slow decay, leading to a steady, predictable reduction in heat output, and consequently, a gradual decrease in available electrical power over time. This inherent power decay dictates the ultimate lifespan of the mission, a fundamental principle of long-duration deep space exploration as understood by engineers at the NASA Jet Propulsion Laboratory. The declining power budget necessitates difficult, strategic decisions by the mission team, particularly regarding the operation of Voyager 1's scientific instruments and core engineering systems. As the electrical output from the RTGS dwindles, power management becomes a critical discipline. Instruments that once operated simultaneously must now be powered down, one by one, to conserve the diminishing energy reserves. This process began years ago, with less critical instruments being switched off to ensure the continued functionality of those deemed most vital for interstellar science. Each decision is a careful balance between maximizing scientific return and ensuring the spacecraft maintains enough power for essential operations, such as heating critical components and maintaining its communication link with Earth. The sequencing of these shutdowns reflects an ongoing, dynamic assessment of scientific priorities and the spacecraft's health, a challenging optimization problem that evolves with every watt lost. Compounding the issue of dwindling power is the ever-intensifying challenge of deep space communication itself. As Voyager 1 relentlessly increases its distance from Earth, the round-trip light time for signals continues to grow. This phenomenon, governed by the constant speed of light and the increasing separation between the spacecraft and our planet, ensures that every command sent from Earth takes progressively longer to reach Voyager 1, and its telemetry takes an equivalent time to return. This introduces significant operational constraints, demanding highly precise scheduling for the deep space network, and requiring mission controllers to plan command sequences with an understanding that responses will not be received for nearly 2 full days. Such propagation delays fundamentally alter the rhythm of interaction, moving beyond any semblance of real-time control. Furthermore, the integrity of the communication link suffers from progressive signal degradation over these astronomical distances. The strength of a radio signal diminishes drastically with distance, adhering to the inverse square law. By the time Voyager 1's approximately 23-watt signal traverses billions of kilometers, it is incredibly faint, arriving at Earth as an almost imperceptible whisper against the cosmic background noise. This diminishing signal-to-noise ratio presents a constant battle for the deep space network. Specialized techniques and advanced receiver technology are employed, including the use of massive 70-meter antennas and cryogenically cooled, low-noise amplifiers. to capture and amplify these attenuated signals. Sophisticated digital signal processing algorithms are then applied to extract the meaningful data from what would otherwise be indistinguishable static. These challenges in discerning faint telemetry demand continuous innovation in antenna tracking, receiver sensitivity, and data reconstruction, reflecting decades of advancements in deep space communication protocols. The physical realities of power decay and signal attenuations fundamentally define the operational lifespan of Voyager 1. Despite the formidable challenges posed by its extreme age and immense distance, the mission team at the NASA Jet Propulsion Laboratory continues to demonstrate extraordinary engineering resilience in their relentless efforts to prolong Voyager 1's scientific return. This ongoing commitment involves a meticulous balancing act of power management, instrument prioritization, and adaptive communication strategies, pushing the boundaries of what is possible in deep space operations. The ingenuity applied to this extended mission phase is a testament to the dedication of engineers and scientists who have overseen the spacecraft for decades, often relying on legacy knowledge passed down through generations of mission staff. One of the most critical aspects of this resilience lies in the strategic power management of the dwindling electrical output from the radioisotope thermoelectric generators. With a constantly decaying power budget, the mission team faces difficult decisions regarding which instruments to keep operational and which to power down to conserve vital energy. These are not merely technical adjustments, but involve careful scientific trade-offs. For instance, in recent years, engineers have ingeniously repurposed heaters, initially designed to keep certain instruments warm, to instead power other crucial components, eking out every last available milliwatt. This creative problem-solving extends to the software itself, with updates and tweaks made from billions of miles away to optimize system efficiency and extend the lifespan of critical components. Such adaptive engineering is a hallmark of long-duration missions, a process continually refined since the earliest days of interplanetary exploration, as evidenced by similar life extension protocols for missions like Galileo and Cassini during their extended phases. Maximizing data collection under these constrained conditions requires constant re-evaluation of scientific objectives. The remaining active instruments, such as the plasma wave subsystem, the cosmic ray subsystem, and the magnetometer, are carefully managed to gather the most impactful data from the interstellar medium. Decisions are made based on the most pressing scientific questions regarding the Heliopause and the surrounding galactic environment, ensuring that even with reduced capabilities, Voyager 1 continues to deliver unique and irreplaceable information. This iterative process of instrument management, where instruments are cycled on and off or run at reduced capacity, is a core aspect of resource allocation in an energy-starved environment, aiming to capture fleeting phenomena or long-term trends even as operational parameters narrow. The communication challenges, already profound due to the immense distances, demand continuous innovation from the deep space network. As the signal from Voyager 1 weakens further, the DSNN's large antennas and ultra-sensitive receivers become even more critical. Engineers are constantly refining the signal processing algorithms and techniques to enhance the signal-to-noise ratio, effectively turning up the volume on the faint whisper from interstellar space. This includes sophisticated error correction codes, which add redundancy to the data stream, allowing for successful reconstruction even when parts of the signal are lost or corrupted by cosmic background noise. The ability to extract coherent data from a signal that is many orders of magnitude weaker than a cell phone transmission underscores the remarkable advancements in radio astronomy and telecommunications achieved by facilities like those operated by the NASA Jet Propulsion Laboratory. Despite these extraordinary efforts and the unwavering dedication of the mission team, The ultimate conclusion for Voyager 1 is an inescapable reality. The mission will eventually come to an end when the power levels from the RTGEs drop below the critical threshold required to operate essential systems, such as the attitude control thrusters needed to keep the antenna pointed at Earth, or the fundamental circuitry for data transmission. While the exact date remains uncertain, based on current decay rates and power projections, mission personnel anticipate that sometime in the next decade, key scientific instruments will cease functioning, followed by the eventual loss of the ability to communicate. The silence from Voyager 1 will not be a sudden event, but a gradual fade, as one system after another succumbs to the lack of power, rendering it a silent, drifting relic of humanity's furthest reach. Yet, Voyager 1's legacy will endure far beyond its operational lifespan. Its pioneering journey into interstellar space has fundamentally reshaped our understanding of the heliosphere and the galactic environment beyond. It carries with it the Golden Record, a symbolic message from humanity to any potential extraterrestrial intelligence, a testament to our curiosity and our place in the cosmos. More profoundly, Voyager 1 stands as a potent symbol of human ambition, resilience, and the relentless pursuit of knowledge. It represents our species' intrinsic desire to explore, to push boundaries, and to understand our universe, inspiring generations of scientists, engineers, and dreamers to look up and wonder. The mission's graceful decline serves as a powerful reminder of the finite nature of even the most ambitious endeavors, while cementing its place in history as one of the most significant achievements in space exploration. The unwavering dedication of the NASA Jet Propulsion Laboratory and its engineers ensures Voyager 1 continues to deliver unparalleled scientific data, even as its historic mission gradually approaches an inevitable conclusion. Voyager 1's incredible journey into interstellar space, powered by engineering resilience, highlights the profound challenges of sustaining communication across billions of miles. As its faint whisper gradually diminishes, the data it continues to send from the cosmic frontier offers unparalleled insights into the universe beyond our sun's reach, reinforcing our deepest curiosity. This mission, a triumph of human endeavor, underscores the delicate balance between technological longevity and the relentless march of time. As we reflect on Voyager 1's remarkable voyage, we invite you to Dissect Official for more explorations into the farthest reaches of science and engineering. Considering the profound challenges and eventual end of such missions, what do you believe is the most significant philosophical lesson humanity gains from pushing the boundaries of what is technologically possible? Thank you for joining us on this journey to the edge of forever. Until next time, we'll continue to explore the cutting-edge technologies enabling future missions to uncharted cosmic territories.